Some of you guys have been asking for an FMA walkthrough, and here it is. We're going to do the 2019 FMA B. It's going to be epic. Hello everybody, I'm Carrara, and today we're going to be doing the FMA 2019 B, and I haven't done this one before, ever. Because last year, my school only offered A, so we only took A, and I haven't really practiced on this one yet, so this is going to be like a completely live, so I've never even seen these problems before. So, let's see how it goes. 75 minutes on the clock. Alrighty, let's get it. 1. A uniform block of mass 10 is released from rest from the top of an incline of length 10 meters and inclination 30 degrees. Okay, coefficients, blah blah blah. The end of the, okay. How much energy is dissipated due to friction? So static friction doesn't matter, right? Because it's gonna go down, right? Static friction can't do any work because it's static, so it's not moving. So we could just do, how long, so length 10. Okay, and inclination 30. Well, okay, so 30 degrees. So that means the force of friction is going to be mg cosine 30 degrees times 0.1, and then the work is just going to be times 10 meters. So what is that? How much is m again? It is 10. So 10 times cosine 30 is time, well, we gotta do cosine, okay, no, let's do this. Do times 3 over 2 times 1. Okay, so 86.6, which is 87B, nice. 2. So 3 cubical blocks of the same volume are made out of wood, styrofoam, and plastic. When the plastic block is placed in water, half of its volume is submerged. If the wood block is placed in water with the plastic block on top, the wood block is just fully submerged. Similarly, if the styrofoam block is placed, same volume, okay. If the styrofoam block is placed in oil with the plastic block on top, the styrofoam block is fully submerged. Okay, so density of oil is 0.7. Okay, so basically we know that that 1/2 V times rho G water G is equal to weight of plastic. Okay, and then we also know that weight of V times rho WG is equal to weight of wood plus weight of plastic, and then we know that volume times rho WG is equal to weight of plastic plus weight of styrofoam. Okay, so now we have to find the ratio of the weights, basically, because they have the same volume, so the ratio of the density is just the ratio of the weights. Okay, oh wait, this should be rho oil. Okay, so we can literally just subtract this, or actually, let's plug this in, so then we get that WW is equal to also 1/2 V times rho WG. Okay, and then that means that in here, if we plug this in, it's going to be 0.7 minus 1/2, so 0.2 rho WG is equal to WS. So if we divide these, we get, we want a ratio of wood to styrofoam. So we divide 1/2 by 0.2, wait, this should be V. 1/2 over 0.2 is what? 5 halves, right? Yeah, 5, wait, no, what? Is it? So 1/5, okay, yeah, this is 5 halves, so it should be A, nice. Alright, 3. 2 springs of spring constants K1 and K2 are connected in series and stretched, as shown in the figure below. Okay, so basically we know that K2 times X2 is equal to F, and then we know that K1 X1 is also equal to F, and then we want to find the ratio of 1/2 K 2x squared over, no, the other way around. Okay, so K1x squared, x1 squared over 1/2 K2x2 squared, and then this is just going to be equal to, oh, so we need to find it in terms of, okay, so we know that x1 is equal to, so x2 is equal to f over k2, and then x1 is equal to f over k1. So if we plug that in here, we basically get, this becomes 1 over k1, and then this becomes 1 over k2, so we basically get k2 over k1. Because the f basically cancel out, so that should be C. Nice. 4. Consider 2 identical masses that interact only by gravitational attraction to each other. If one mass is fixed in the plane and the other is released from rest, then the 2 masses collide in time t. Okay, if both masses are released in rest, then they collide in what? Okay. This is kind of hard. Oh, wait. Okay, so if we do like an accelerated reference frame, right? So originally it's like this, right? So so it's originally like this. So there's a force of gravity, okay? And then if we do the second one, there's a force on this guy and a force on this guy, alright? So if we do the reference frame thing, then we basically get this 2F. So that means that any point in time it's accelerating twice as fast, so that means it'll take how much less time? So basically we have 1/2 at squared is equal to distance. So if you have twice as much acceleration, that means that your time is going to be divided by 2, or your time squared, so it should be over root 2, so it should be d. Wait, is that valid? Because like your force, basically originally it looks like it starts at a certain thing, and then as you get closer it increases, like, how would it increase? So as you get closer to your r, and then as r decreases, it goes like that. So if you multiply by 2, you're basically just multiplying everything by 2. So the area just twice as much. Okay, yeah, I think we're good. So let's just move on. 5. The density of the Earth increases gradually from around 3 grams per centimeter cubed at the crust to 13 at the core. Okay. So basically the way that gravity works is it only cares about the sphere on the inside, right? So if you start at 13 grams and then you go outwards, the rate at which your mass is increasing decreases, right? Or actually, the acceleration for sure increases, so we could, it always will increase, so we could for sure get rid of E and D. Oh wait, but it has to go down eventually once it reaches outside of the planet. Because once you get outside the crust, it's gonna start going down, because you're keeping the mass the same, but you're getting further and further away. So this is literally just, but it could be this one too. Because maybe if you go out, your mass is increasing by less than the amount at which your thing is increasing. Your distance is increasing. Well, basically you know that dm is equal to dr times 4 pi r squared times density. Well, okay, at the very center, at distance r equals 0, we know for sure that your acceleration is going to be 0. So d is out of the picture, it has to be e. Okay, we're good. Wait, actually distance 0 doesn't have to be 0 though? Yeah, it does have to be 0, so I guess that makes sense. Alright, 6. A very long cylinder of dust is spinning about its axis with angular velocity w at steady state. Okay? And then r be the distance from the axis. If the dust is only held together by gravity, the density of the dust is proportional to what? Okay, so you know that the acceleration has to be rw squared. And basically your gravitational acceleration is going to be the mass of the cylinder inside, like less than a certain particle of dust over radius squared. So acceleration is going to be gm over r squared, where m, and then we want this to equal to rw squared. So basically that means that m is equal to r cubed w squared. So basically the mass has to be proportional to r cubed. However, if density is constant, it's only proportional to r squared, because as you increase the area, it's the area times the height, and the height is constant. So we have to have that the density is equal to 4 pi r squared, so we need the density to be proportional to r. Okay, so 6 should be d. 7, so it's directly under the left wire, so that means that, like, the tension shouldn't be affected, right? Because basically, by Pascal's law, a pressure is exerted in like all directions. So basically the pressure on the overall box is going to be exactly the same. So it shouldn't be different. But it does have to be increased as well, because it has to support the weight of the boat. So it should be B. Tension increases equally in both wires. 8. Scale is calibrated so that it gives a correct reading when sitting on the ground. A person holds the scales and presses it on both sides with their hands, putting up on the bottom with the left hand and down on the top with the right hand. Okay, so their left hand, which is on the bottom, exerts a force of 200 newtons, okay? Which means that the right hand has to exert a force of 200 minus the weight. So 200 minus 50, yeah. So 150 is how much the other one has to exert. So that means you have like, okay, so when a scale's on the ground, right? Its mass is going down, it has a normal force on it, and then it has a thing that's going down, and it basically measures the thing that's over here, right? So basically, we're measuring how much force the right hand is putting on it. So that means that if we exert a 150 Newton force, that means our weight that's going to read is 115, so it should be a nice 9. Let's do it. Alright, so a light board of length L is hinged to a vertical wall. A solid ball of weight G and radius R is held between the wall and the board by a force F applied perpendicular to the board. Both the wall and the board are frictionless. The angle between the board and the wall is 60 degrees. Okay, so now we just have to draw a bunch of forces, I'm assuming. So basically the forces on this is going to be a normal force over here, a normal force over here, and then the weight of this is G. So let's say this is Fn1, this is Fn2. We know that Fn1 is equal to Fn2 cosine 60 degrees. Okay? Then we also know that Fn2 sine 60 degrees is equal to G. We also know that if the rod exerts Fn2 on the circle, then it's going to have to exert Fn2 back on the rod. And the rod is in equilibrium, so basically the torques have to be cancelled out. So now we just have to find the ratio of the length. So if this is R, and then this is 30 degrees, then that means that this length over here is R root 3 over 2. No, what? R over root 3. No, R root 3. Okay, yeah, that's what it is. R root 3, that's what it is. So basically, this length is R root 3, and then, so basically we have that Fn2 R root 3 is equal to FL. So we know what Fn2 is, we can just plug it in, and we basically get that F is equal to G over GR root 3 over sine 60, which is root 3 over 2, so over root 3 times 2, so that's just 2GR over L, because we had to divide by L, I forgot, yeah, so over L, so it should just be B, nice. Alrighty, a ball of mass M is rolled in a bowl bolted on a cart. The bowl and the cart move together and have a combined mass MC as shown in the figure. Initially, the cart moves to the right with speed v 0 with respect to the ground, while the ball is at rest with respect to the cart. The ball then slides down to the bottom of the bowl. When it reaches the bottom of the bowl, it moves with velocity vv with respect to the cart. At this instant, how fast is the cart moving with respect to the ground? Okay, so this is just like, you could use center of mass, because you know that the center of mass of the system is going to be constant throughout. So initially, if the cart is moving v0 to the right, then this ball is also starting v0 to the right. Does it say that it starts at, rest with respect to the cart? So basically, our initial center of mass velocity is just going to be v0. Okay, and then when it reaches the bottom, it has no vertical velocity, but it has all its horizontal velocity. So basically, what we could do is we could say that m, or actually, let's say that v is the our answer, basically, how fast the cart is moving relative to the ground. So that basically means that our m is going to be moving at, or our small m is going to be moving at v plus vb at the bottom relative to the ground. So our center of mass velocity is going to be m times v plus vb plus mc v all over what? It should be all over m plus mc, and then this should equal to v0. So if we just solve for v, we get our answer. So we basically get m times v0 minus vp plus mc v0 over m plus mc, which is the same thing as, vb, not vp. Dude, my handwriting is beautiful. Okay, that's the reason why. It's just so beautiful I can't read it. Anyway, so that is the same thing as D, so we're good with D. Nice. Alright, whoops. Consider a flat uniform square, how does square become sphere, of mass M and side length L. Cut a circle out of the sphere. Dude, what is a sphere? Okay, square that has a diameter equal to the length of the side of the square with the same center of the square. Determine the moment of inertia of the remaining shape bound an axis through the center and perpendicular to the plane of the square. Okay, so the first thing we got to do is find out what the moment of inertia of a square through this axis is gonna be. Now I feel like we shouldn't have to integrate this, but I did not memorize the answer for this, so I guess we'll have to integrate it. It's gonna be epic. So basically, you just do two integrals. You basically do this. Let's say that this is the density, okay, then you multiply by x squared plus y squared, times, yeah, x squared plus y squared, and then dx dy. And then this is 0 to L, and then 0 to L. Or actually, wait, what? No, 0 to L over 2. So we could basically find it for this thing, and then it's the same for the rest, so that's what we got, 0 to L over 2. Okay. Okay, we could just do negative L over 2 to L over 2, and then we're good. Okay. Alright, so basically the integral becomes f of, oh, we could take out this, and then this becomes x cubed over 3 plus y squared x dy, and then we could integrate that again, and we get sigma times x cubed over 3y plus y cubed over 3x. Oh, wait. So we first have to plug in our things. So if we plug in L over 2 to negative L over 2 for this, we basically get what? L over 8, L plus, okay, so it should be L over 12 plus L cubed over 12 plus y squared L. Okay. And then we integrate this again, and we basically get L cubed over 12y plus ly cubed over 3. And then this should give us L over 2. Okay, so this should give us L to the 4th over 12 plus L to the 4th over 12. And then that should just give us L to the 4th over 6 times the sigma. And then this is just equal to L squared over M over L squared. So that's just going to be ML squared over 6. So that is the moment of inertia for a square. If you memorize this would be a lot easier, but I did not memorize it, so I guess we had to derive it. Okay, so we have ML squared over 6, and then you had to subtract out the circle. So the circle's diameter is just going to be, the circle's radius is going to be equal to L over 2, so pi L squared over 4 is the area. And then it has the same density, so its weight is going to be m pi over 4, and then we multiply it by a circle is going to be 1/2 mr squared, so 1/2 times this times L over 2 squared, and then we subtract that from this. So we basically get 1/6 minus 1 over 32 pi. Yeah, so A. Cool. That took way too long. Should not have wasted so much time on that. Anyways, but we're chilling on time. Kind of. Alright, so planets A and B have masses ma and 2mb. They orbit a star. In circular orbits, the radius RA equals 3RB. Circular orbits are so much easier than other types of orbits, so this should be fine. Okay, so basically, let's just write the equation. So we basically have that V squared over RA, VA squared over RA is equal to, so they basically orbit a star, so we could just say GM over RA squared. So this basically says that VA is equal to root GM over RA. Okay, and then this is the same for the B. So our kinetic energy is just going to be 1/2 times MA times GM over RA, and then that's going to equal E. And then we know that LA is just going to be MA VA root GM over RA times RA. Okay, so now we just have to compare the ratios. So this is for A. Okay, and then if we plug in the B stuff, we basically get 2mb root gm over 3rb rb. So this is basically going to be, what? 3rb, whoops, okay. So the ratio is going to be 2 root 3 of this. Oh wait, what? Oh no, this is MA in terms of MB. Okay. So basically, LA is going to be equal to 2 root 3 LB. Okay. And then say, we could do the same thing for this. We basically get that MB times GM over 3RA. So that's 2/3 of this. So basically, EA is equal to 2/3 EB. So EA is less than EB, but LA is greater than LB. So C. 13, let's do it. Holy, that's a fat problem. Okay, let's see. A water hose is at ground level against the base of a large wall. By aiming the hose at some angle, squirting water at speed v, one wets the region on the wall as shown below. If the speed of the water is double, what is the new region that can be wetted? I don't know how this works. What? So that's a very ground level. Well, okay, so the water is not going to go up, but it could, like, come down. So the height should not change. The water just can't, like, suddenly go up the wall, so that doesn't make sense. But none of them have the same height. What? But how could the water just go up? That doesn't make sense. Huh. Okay, I have no idea. Let's skip it. Alright, a ball is launched at speed v at an angle theta above the horizontal towards the vertical wall a distance L away. Alright, so it bounces elastically off the wall and falls back to its launch point. So basically, if it's gonna fall back to its launch point, it literally has to, like, hit the wall, like, straight on, like, in that direction. Because if it did it in any other direction, it would be, like, upwards, and then that would, like, not work because it would go past. So it has to literally hit it straight on. So that basically means that our Vy is going to have to be 0. So we know that V sine theta minus gt is equal to 0. Okay, so that basically means t is equal to V sine theta over g. And then we know that V cosine theta t is equal to L times t, yeah. And then basically we want initial speed. So we get V squared sine theta cosine theta over g is equal to L. And that basically says that V is equal to root GL or 2GL over sine 2 theta, which is E, very epic. 14. Oh, that was 14. Whoops, we skipped 13. 15. Alright, so it's attached to a string of length 2r. Person swings it, says their hand is in a circle like that, and then the mass is at an angle of pi over 2. Oh, what? Oh. Okay, so basically, the object has two forces on it. It has this force, and it has this force. Or no, this force, which is air resistance. And basically, we want the ball to only have centripetal acceleration. So first off, we had to figure out how much centripetal acceleration it needs, and we know that the angular velocity is 10 radians per second. So basically, our centripetal acceleration of the ball is going to be 2 times 10 squared, so equals 200. So that's our centripetal acceleration. Alright, so now we just have to find this angle over here, so we could find this, and then we could find this, and then we could find that. So basically, you have 2 meters, then you have 3 centimeters. Oh wait, no, this is 2 meters, and then this we don't know yet. So basically, sine theta is equal to 0.03 over 2. So if we take the sine inverse, we get theta, then we use tan to get this, and then that's going to be equal to the air resistance. So we basically do 200 times tan of sine inverse, arc sine, 0.03 over 2. So that's going to be 3 newtons. That's not even an option, bro. Oh, mass? Does mass matter? Oh, wait, yeah. So mass matters, so we need to find the force. So it's going to be times 0.1. So times 0.1 is 0.3, which is D, epic. 16. Alright, so we have a hoop of radius r launched to the right, initial speed v0 at ground level. As it is launched, it is also spun counterclockwise at an angular velocity 3v0 over r. The coefficient of kinetic friction is that. So how long does it take to return to its starting position? Epic. So basically we know that it has v0 this way, and the only force acting on it is friction, right? But friction will stop acting on it if it starts rolling without slipping. Okay, so now we have to know whether it starts rolling without slipping. Well, guaranteed does start rolling without slipping at some point, right? Alright, so let's just figure this out. Oh, but like the friction changes direction on its way back, right? Okay, yeah, so this does start rolling without slipping, so we gotta figure that out. So basically we have that alpha is equal to FR over MR squared. FR over MR squared. Okay, so that basically means that alpha is equal to F over MR. Okay, so then we get 3v0 over r minus F over MRT, and then we make this equal to, and then what? So this is angular acceleration, so we want actual acceleration, which is just going to be equal to m over f, or f over m. Okay, and initially starts with 3v0 minus, so we're doing it in this direction. So basically it's going to be fmt minus v0, because it initially starts in the opposite direction. Wait, so yeah, this slows down, and this also slows down. No, but okay. So this should be right. So originally they're on opposite direction and we want them to come together. So if we just solve this, we should get our t. So we basically get 3v0 minus f over mt. Okay, so 4v0 is equal to 2f over mt. So t is equal to 2v0 m over f. Okay. And then once it starts rolling without slipping, it's not going to accelerate anymore. So what's its velocity at this point? So it's going to be 2v0 minus v0. So it's basically going to be going v0 in this direction after it stops rolling without slipping. Wait, okay, let's just try it if we assume that friction is always acting on it. Oh, we do know what friction is. So this is just going to be g mu k. And if we basically find out how far it's gone, so 1/2, v0 t. So 2v0 squared m over g mu k. So minus 1/2 times, what's our acceleration? Minus g mu k, or mg mu k, so this should be, okay. Minus 1/2 g mu k times this squared. So that's just gonna be 4v0. Oh, so literally this is the time because it really returns exactly back to its position once it starts starts rolling without slipping. So this should be your time. 2v0 over mu kg, which is b. Okay, well the answer to the previous question, b for uniform disk with the same coefficient. What? This is just bad grammar. So the thing that would change is our alpha here, and then this would basically become 1/2. So this would become 2, and then this would become 3. So it'd be 4/3 v0. So the torque is the same, so that's not the problem. It does start to so this is the point at which it like. Wait, so if we plug this in here, so it's gonna have v0 over 3 in the opposite direction. So we'll get to its thing. So d, yeah, 17d, it stops slipping too soon, because if we plug it into this thing again, our v0 t is gonna be different, so it's gonna be 4/3 here, and then this would be 16 over 9, and then that would be 8 over 9, which is smaller than this, so it would still have to come back a little. So yeah, D. Okay. 18. How much time do we have? We're spending a lot of time on this one. Okay, 30 minutes. You are predicting the time for a car to complete a race. The car begins with initial speed v0 and maintains a constant acceleration a throughout the race. Both v0 and a have independent uncertainties of 10%, which contributes greater to your uncertainty, to your estimate of time for the car to complete the race. So let's just figure it out. So basically, we have our total distance, d, is equal to v0t plus 1/2 at squared. So sad, god dang it, it's gonna be a quadratic. Alright, let's just see. So we get negative v0 plus or minus root v0 squared minus 1/2 a plus 4 plus 2ad over 2a, so that would be over a. So basically, v0 contributes here. Well, okay, let's think about it. So if we draw our diagram, let's say we have this, then basically you have your v0t over here and you have this. So in a short race doesn't matter. It shouldn't matter whether it's short or not. It's a race. So a is basically going to be like, oh, it either ends here or it ends here. But for v, it's like here or here. Okay, I feel like it's uncertainty in v0 because you can see like it's a lot more massive. But if time is short, then a is small. But if time is really big, then a could get crazy, man. Okay, I think it should be v0 in short races, and yeah, let's go with a. Alright, a physical pendulum consists of a mass on one end of a massive rigid rod that can pivot about an opposite end. Assuming the oscillations have amplitude 90 degrees, which of the following graph shows the total mass acceleration of the mass as a function of angular position theta? Well, I mean, why can't it, wait, what? Isn't it literally just like, so this is g, but then this cancels out, so this is going to be g cosine theta, right? No, sine theta. Is it not? So sine theta is going to be like, wait, what? None of these are sine theta, though. Well, okay, at the very bottom, oh, wait. Centripetal acceleration. Hold up. Centripetal acceleration is a thing. So it's never going to go to 0. That doesn't make sense. So it's not this one. It's not this one. Okay, so let's think about it. So what's the velocity going to be? So you basically have that mg times cosine theta times 1 minus r. No, what? No, sorry. mgl times 1 minus cosine theta. Or 1 minus sine theta, actually. No, cosine theta. We're good. So it's 1 minus cosine theta is equal to 1/2 mv squared. So v is, so then we want v squared over r, which is going to be g times 2g times 1 minus cosine theta. So that's just this over here, centripetal acceleration, and then we have g sine theta here. So we square this and we sum them together, you basically get 4g squared times 1 minus 2 cosine theta, and then this gets squared, okay, and then you get plus 1 minus cosine theta squared plus g squared sine squared theta. So this is quite clearly not b, okay, and then this over here might be it, and this amount over here might be it. So let's try it. So this one says that at 0 and 90 is the same, so let's try it. So 0 would be, this is 1, so this is going to be 0, and then this is going to be 1, so g squared. And then at 90, this is going to be 0, and this is going to be 4g squared, so that's not the same. So, wait, what? Yeah, so basically it's saying it decreases like this, from 4g squared, oh, this is acceleration squared, so yeah, it goes from 2g squared to g. Oh, nice, A, cool. 19A, 20. How much time we got? 27, okay, pretty good. A block on a ramp is given initial velocity v0 upward along the ramp. It slides upward for a time tu, traveling some distance, and slides down for a time td until it returns to its original position. What is td in terms of tu? Okay. Oh, I love these problems. No, I'm kidding, I don't love these problems. But basically what you got is you got, on the way up, this is friction this way, and then also mg, mg is down. So basically acceleration due to friction is just going to be g cosine theta mu k, which is times 0.5. Well, let's just do mu k. Okay, and then that also means, so that means the total downwards acceleration is going to be this plus g sine theta. So basically tu is just going to be, we could do v0t, or no, we could just, wait, what? Well, basically we know that we can use the formula vft like minus, so plus 1/2 gt squared, or 1/2 at squared. So 1/2 times g, 1/2 g times cosine theta mu k plus sine theta is equal to the distance. Alright. And then the other way is the same thing, but it's 1/2 g times cosine theta mu no, the other way around. Sine theta minus this. Okay. So basically that says that d is equal to this, and this is 0 by the way, so it's basically going to be, so this is t squared, whoops. So d is constant, so basically this is t1, tu, and then this is td squared is equal to d. Okay, so we want to find the ratio of these two, so we could divide them by each other, and you get tu, oh wait, we want td, so td over tu squared, okay, td over tu squared is equal to this one over, wait, what? Yeah, it's equal to tu squared thing, okay, so 1, so that would be cosine theta mu plus sine theta over sine theta minus cosine theta. Because it makes sense, right? Because the downtime is going to take a lot longer because friction is opposing your acceleration. But the uptime is going to take a lot less time because you have more acceleration. So 0.6 L, and then this is L. So it's basically going to be the triangle looks like this, 0.8, 0.6, and then 1. So basically cosine theta is just going to be what? Cosine theta is going to be 0.8. So 0.4 plus 0.6 over 0.6 minus 0.4. And that is just equal to 1 over 0.2, which is equal to 5, which is E epic. No, but that's squared, so we had to square root it, so C. Poof, that was a close one. Almost got that wrong. How much time? Come on. Okay, 22 minutes. Gotta go fast. Okay, so an empty freight car has mass M. A chute above the freight car opens and grain falls at rate R. The grain falls a vertical distance h before hitting the car without bouncing up. How much normal force is exerted on the freight car from the rails at time t after the grain begins to hit the bed of the car? Okay, so it's not moving, so we don't have to worry about how fast it's moving. And then we also know that your mass is equal to the first mass plus RT. Okay, so we know the normal force is going to have to, so basically, okay, so you have your cart, right? And the cart is exerting impulse on all these particles. And basically impulse, delta P over delta T is equal to force. Basically we got to find delta P, and then this force is also exerted on the cart, which has to be counteracted by the normal force. So normal force is equal to M plus RT times G plus this thing over here. So let's just find that. So how much speed does it have? It's going to be root 2 GH, is the speed of each one. and then the speed times r. So that is basically going to be your force, r times root 2gh. So we add plus r times root 2gh, and this should be our normal force. So E is the right one. Nice. We're zooming through this. All right, 22. Not really. We're kind of late, but we got this. All right, the bruise threshold for a fruit is the largest height it can be dropped without bruising. The bruise threshold of a 0.2 kilogram apple on steel is 10 centimeters. Suppose that it always takes 0.1 seconds after the impact for the apple to fully stop, and that 4 centimeters. Okay, so basically we just gotta find the force. So basically we could do our impulse thing again. So it falls 10 centimeters, right? So that's gonna be root 2 times 10 times 0.1 is basically equal to our v. Okay, and then we want mv over t. So 0.2 times root 2 over t, which is 0.1. So that's our force, and then that's times 4 centimeters squared, which is 4 over 100 squared to get meters squared, and this is just equal to our pressure. Okay, so if we just plug this in, we should get our answer. So 0.2 times square root 2 over 0.1 over 4 times 100 squared. So 7071, which is approximately 7,100, which is C. 23, let's go. Okay, so a train travels 360 kilometers per hour on an almost straight. This track is slightly sinusoidal with a vertical amplitude of h over a 1 kilometer distance as shown in the figure. If the maximum tolerable vertical acceleration of the train is set at 0.1 meters per second, what is the maximum allowable size of h? So let's just write an equation for the h, like the vertical component of its displacement. So basically y is equal to h times sine theta sine x. Wait, what? Does it have it has a velocity too, so we could just do sine t. Wait, what's the period? So the period is 1 kilometer over 360 kilometers per hour. So basically your period is 1 over 360, but we had to convert it to seconds, so that's basically going to be divided by another 3,600, or no, multiplied by 3,600, so that's going to be 10. So our period is 10. So basically it's just going to be 2 pi over 10 times t. Okay, that right? So basically acceleration is going to be dy over dt is equal to h cosine theta. Oh yeah, so 2 pi over 10, so pi over 5 h cosine 2 pi over 5 t, and then if we plug it in again, we get d squared y over dt squared, which is acceleration is equal to pi squared over 25 h times negative times sine pi over 5t. Okay, so now that we have this, we basically had to set this equal to 0.1 is equal to pi squared over 25 h times sine pi over 5t. And basically this maximizes when this is equal to 1, so we can just ignore that, and then if we plug this all in, we should get our answer. 25 times 0.1 over pi squared. So that gives us 25 centimeters, which is B. 24. 16 minutes. Okay. A uniform rope of length L and mass M passes over a frictionless pulley and hangs with both ends at equal height. Okay. If one end is pulled down a distance x and the rope is released, the acceleration of that end at this instant will be. Okay. So originally it's like this. L over 2, L over 2. So then if you pull this x, then this L over 2 plus x and this L over 2 minus x. Okay, so your mass on this side is going to be L over 2 minus x over L times m, and then that's going to be our mass, and then our force is going to be that. And then on the other side we have L over 2 plus x times mg over L. Okay, and then if we divide this by m, we should get our total acceleration. I wish we could add them, then it would cancel out nicely. Actually it does cancel out nicely anyway, so we basically get that it is gonna be 2xg over L. Nice. But I feel that's too easy. No, I think that's right. I think that's how I always do it, so it should be right. E. Frictionless pulley, so the pulley doesn't matter. Wait, that also makes sense because basically you have like 2x over here, additional 2x weight on this side. So it's basically as if there's just a 2x weight here that's pulling like a system of like m. So then, yeah, okay, that just makes sense. Okay. So E, let's go. Okay, 25. Last question. And then we'll go back to 13 and see if we could think of anything epic. How much time we got? Okay, 13 minutes. A student makes an estimate of acceleration due to gravity by dropping a rock from a known height and measuring the time t it takes to hit the ground. What of the following situations will lead to the smallest value of relative uncertainty? Okay, so let's just figure out what it is. So 1/2 gt squared is equal to h. So basically your g is just going to be 2h over t squared. So your relative uncertainty is going to be 2h, so 2 times the uncertainty of h, okay, and then this squared, so sigma h, plus the uncertainty of t squared, which is just going to be root 2 of that. So then it's root 2 of sigma t of this squared. And then the root of that is your total uncertainty. Okay, so if we plug this in, we basically get the 0.1, root 2 times 0.1 is what, no, we just get 2 times 0.1. So this, so A has an uncertainty of 0.2, or yeah, 0.2, and then this one will have an uncertainty of 0.1 times root 2, which is what? Which should be 0.14. And then C has uncertainty of what? We can plug this into our calculator. So we can do squirt of 2 times 4 times 0.05 squared plus 2 times 0.05 squared, which is 0.122. So this has 0.122, so that's just like straight up the best, epic. So it should be C. Okay, next. 26. Oh, what? No, 26. Okay, 13. We're going back to 13. Let's do it. Okay. How do we do this? If we have time after this, I'm going to check my other answers. So water goes at ground level against the base of a large wall. So this is the very bottom. Okay? And then you aim it at some angle. Oh, so you said angle, so it would hit higher. Oh, so we could think of, that makes so much more sense. Okay, so basically like this. So if your angle is the same, but you double your velocity. Okay, so let's say this is v. So v0 cosine theta is equal to the distance, okay, d, and then times t, and then v0 sine theta t minus 1/2 gt squared is equal to h. So basically, if we double, so let's just solve it first. So we basically get that v0 sine theta d over v, so this is tan theta d. Tan theta d is minus 1/2 times g times t squared, which is gonna be gd squared over v0 squared cosine squared theta is equal to h. Wait, that's not, so the height's not gonna be exactly doubled, right? In fact, shouldn't it be decreased? So the constant, no, so I did something wrong, I'm assuming. Well, I know for a fact that it's gonna be higher, so it's gonna be somewhat higher, and it should be, if it's double the height, it should be double the width. But I don't think it's, what? Alright, so, wait, so what's wrong with this? So v0 cosine theta is equal to the distance from this to the wall, okay? And then v0 sine theta is the vertical, and then you subtract 1/2 gt squared. Alright, and then if you plug in t is equal to d over v0 cosine theta, then this becomes tan theta d, so you're subtracting 1/4 of the amount that you're originally subtracting. How does that help at all? Okay, why don't we combine it? Okay, fine, let's say that, like, let's say that it goes straight. So if you double your v0, then you're basically going to double, because this stay the same. Wait, what? No, so, what? So if you double it, it's going to go somewhere like that. So is it going to double or quadruple? Okay, I think it's going to double. So now we just have to think about whether it's going to have the same width or not. But I'm pretty sure that it's not going to, like, it's not going to come down faster. The acceleration is still going to be the same. So if it, like, spreads out like that, then it should come down at the same shape. So it should be B. Okay, I'm going to go with B. That's what I think it is. Alright. Do we want to check our answers? Let's just check it real quick. Do we have, yeah, we have time. But you don't need to watch me. But we'll see. Okay, I might edit this out. Yeah, okay, we're out of time. Let's just check our answers. Okay. Alright, so BACD. Alright. EDB. Or no, 6. What? How did I get 6 wrong? Holy, that's bad. That doesn't sound good. BAB. DAC. 13. Okay, so 13 we didn't know how to. Oh, what? Dimensional and. What? That's what it is? Oh my god. Alright, so 14 EC. Oh my god. This is bad. Oh, just kidding. I was reading the wrong thing. Okay, EDB, DAA, CEC, BER. What? No. Holy, okay. It's okay. 22. Not bad. But bruh, I missed some stupid ones. Okay, let's see what we did wrong. So 25 is, oh, relative uncertainty. Does that matter? Wait, when is it relative? Oh, wait, I forgot. It's relative. Okay, let's just do it real quick. So basically we have that g is equal to 2h over t squared, right? Okay, so we did get our formula. I just forgot my whole formula nonsense. So it's gonna be like, so it's gonna be 2 sigma h over h squared plus root 2 sigma t over t squared. Okay. So if we know that g is equal to 10, then we know that 2h is equal to 10t squared. So h is equal to 5t squared. Wait, why does that make sense? Wait, okay, let's just look at their solution. Okay, so that's what we got. Oh. Wait. Oh. Whoops, I just did it. Wait, what? Okay, so this one does it for real. Oh. I guess the 2 doesn't affect. Okay, we should. Oh no. So this is. Bruh. Okay, I see. So the 2 should go out here. Okay, so makes sense. Yeah, then it makes a lot more sense. Okay. And this should just be 2 over here. Okay, I see. And then which other one did we get wrong? 6 and 13. Very nice. Alright, number 6. How did we get number 6 wrong? Dude, this is the one that I was sure about. Alright, let's see. Okay, I don't get it. Let's look at 13 real quick. So it says I will look at the solution for 6. But first, we gotta see if 13 is dimensional analysis apparently. So height is gonna be v0 squared over g, I'm assuming. And then your oh, bruh. Okay, so v0 squared, and then it's okay. So d. Is d the answer? Yeah, 13d. Okay, makes sense. So 6, what's the problem? Why are they using Gaussian surfaces? But okay, I guess that makes sense, yeah. Alrighty, anyway, that's good enough. 22, not bad. I think I managed my time pretty well. I didn't like spend too much time on anything. I just skipped over the one that seemed like they would spend too much time. Made some silly mistakes, but other than that, pretty okay. Thank you guys for watching. As always, if you enjoyed the video, leave a like and subscribe for more. Thank you again for watching, and see you guys next time.